Good afternoon, everyone. Our next session will be handled by Ramjit Sir, and it's a hands-on session, and will cover BERT embedding algorithm and transformer network. Welcome back, sir.
Thank you, ma'am. Good afternoon, everyone. So, uh, today's session is going to be uh, a discussion on transformer networks and BERT embedding. Then we'll do some experiments using BERT, 2, 3 examples. Okay. So before starting the theory session, I mean hands-on session, I'll give you a brief idea about how the transformer is defined, how BERT is computing the word vectors for each words in a document or corpus, and what are the differences between BERT and other embedding algorithms you have studied already. I believe that you have already uh, discussed or had a session on word-to-vec and other algorithms like fast text kind of algorithms. I don't know what are the algorithms you have already discussed. Okay, so today we will see the BERT and the transformer. Okay, I'll share my screen. Give me a minute. Hope my screen is visible to everyone. Okay, transformer networks and BERT. So the transformer network has revolutionized the NLP research to a great extent. So not just NLP, but the other areas also like image processing, speech processing, etc. So almost all the state-of-the-art models are based on transformer networks nowadays. Okay, transformer is the models, deep learning models based on transformers are the state of the art. Okay, so hope you have already had a session on LSTM, long short-term memory networks. So there are some certain problems with or disadvantages of LSTM networks. So LSTM, as you know, it is a type of recurrent neural network. It is a variant of recurrent neural network which can capture the contextual dependencies in the sentence. Okay. Uh, Compared to the RNN, LSTM uses some logical gates which can be considered as some tabs uh, which can allow the transfer of knowledge between two states in the data. Okay, then in LSTM we don't have any recursive computation, unlike the recurrent neural network, and we have a separate memory cell for computing the or updating the contextual memory for each word or at each time step in the network. Okay, then there are some certain problems with the RNN, which is called as vanishing gradient or exploding gradient, and LSTM's first and foremost application is to resolve that issue. Okay, LSTM can deal with the vanishing gradient and exploding gradient problem, and vanishing gradient or exploding gradient problem is happening because of the lengthy sentences. Okay, if you have a long sentence or a sentence with a more number of words, then RNN won't be able to capture the proper contextual dependencies among the data. But LSTM can do that, okay, with the help of the logical gates. Okay, so there are some problems with LSTM. So since the network contains a lot of logical gates, the number of parameters trained by or learned by the LSTM network is more. So which in turn increases the difficulty of the training method. Okay, then you can understand that compared to LSTM, so RNN, LSTM can deal with the very long sentences or very long dependencies. Okay, but still there is a limit to which the LSTM can learn the contextual dependencies among the words in a sentence. But compared to RNN, LSTM can learn more lengthy sequences. Okay, but if you increase the length of the sentence or length of a sequence, or if you increase the number of words in a sentence or number of characters in a sentence, the network becomes more and more deeper, and it becomes more and more complicated. And the gradient path is basically considered as the training process. Okay, for training a neural network, we use an algorithm called gradient descent. Okay, so that gradient descent path, or the uh, path from the output layer or the error to the input layer, okay, that is going to be a lengthy path, and that again increases the complexity of the network. Okay, then we cannot do any transfer learning with LSTM, because there is no LSTM predefined model, but we can find predefined model for word to vec, fast text, etc. Convolutional neural network pre-trained models are also there, image processing pre-trained models are also there, but it is very difficult to find an LSTM based pre-trained model. So if you want to use an LSTM for an data, you have to start the training from the beginning itself. Okay, and one of the more major issues with LSTM is LSTM, not just LSTM, but with RNN and other variant of LSTM, GRU, gated recurrent unit, is the sequential property. Okay, by birth, LSTM is sequential, or RNN is sequential, or GRU is sequential. Because of that reason, it is difficult, very, very difficult to incorporate parallelism. Okay, so if you want to process the data parallelly, or if you want to process all the words in a sentence simultaneously, then it is not that feasible with the LSTM networks. Because in LSTM, as you know, we take one word and process it and compute some information related to that word, and based on that information, we compute the information for the next word by considering the next word and the previous information, etc. Okay, so that is how it works. RNN takes words one by one, or characters one by one, or input in general one by one. Okay, it cannot process all the inputs simultaneously or in parallel, and because of all these reasons, you can say that LSTM is too expensive to train. Okay, so that is the reason why people have started thinking about having a different network. You can basically find an evolution in this, just like the evolution in the human beings or other animals. You can find an evolution in the algorithms used for dealing with the textual data or sequential data. Basically, before LSTM and transformer networks, RNN, etc., we use in all the NLP tasks. NLP, as you know, NLP means, or if you want to process a textual data, in a text, all the words are connected and all the characters are connected. If you arrange the characters in a proper order, then only you will be able to get a meaningful word. Similarly, if you arrange the words in a proper order, then only you will be able to get a meaningful sentence. So you have to consider that arrangement, so that connections between the characters or the words. So before the LSTM and RNN, we have algorithms like conditional random field, hidden Markov model to deal with the sequential data, and they have a lot of issues like uh, hidden Markov model prediction. The next, if you want to predict the next word, okay, it can use the current word only. It won't be able to uh, process the previous words, okay, or it won't be able to process the previous context, okay, in which that word appears. Okay, so that is the problem with the hidden Markov model. CRF, conditional random field, is a generalized version of hidden Markov model. So there is a limitation for remembering the sequential connections or relationship between the words or characters in the data. So that is the reason the recurrent neural network was proposed, and ARN has a lot of issues like the number of words it, or the length of the context it can remember is less compared to HMM or hidden Markov model. It is very high, but in general, in, uh, in all our sentences, most of the sentences may contain more than 10 words or 20 words. Okay, in that case, RNN fails to capture the long-term dependencies in the data. So that is the reason why LSTM was proposed, and LSTM had a lot of issues. Uh, okay, one issue is LSTM uses a lot of gates. So if you use more gates, then you are going to learn more parameters. Then that was another problem, and that is the reason why GRE was proposed. The GRE is similar to LSTM, but uses limited number of parameters or less number of parameters. But LSTM has some issues, and okay, then or the encoder decoder architecture, which is designed using LSTM, started showing some issues. Then attention mechanism was proposed to resolve those issues. Okay, now people found out that LSTMs and RNNs are not sequential, so it is too difficult to implement parallelism using LSTMs and RNN. So they started thinking about creating a new network. So they finally understand that, they means the people from Google understand that, okay, with the help of some attention mechanism or attention neural network, it is possible to create a network which can process the data simultaneously, or in that way you can bring parallelism in the processing. So that algorithm is called as, or that network is called as transformers. And now many people say that LSTM is dead, because LSTM is no longer used for many applications, because transformers have outperformed LSTM networks in many applications. So now transformers and its variants, different networks are possible, are available, okay, for free usage, okay, based on transformers. And unlike LSTM, you can also find pre-trained models using transformers. Okay, pre-trained models means the network trained over a huge data which can be used for our analysis. Okay, so such networks are available nowadays. Okay, so this is a not a diagram of transformers. Okay, it's for fun only. I put this image. So an image from the movie Transformers. Okay, you can read this paper. Attention is all you need. Uh, so this paper was proposed by people from Google. Okay, Ashish Waswani, Noam Shasir, Nikki Palmer, etc. So all these people are very pioneers in this area. Okay, so you can uh, go through this paper, okay, for understanding more about attention mechanics, sorry, transformer networks. And transformer network, as its name suggests, okay, as the name of the paper suggests, transformer network is completely based on attention mechanism. Okay, so it doesn't contain any recursive connection, or it doesn't contain any RNNs or LSTMs. So the contextual dependencies, or the connections between, or the relationships between the words and characters, are captured using attention mechanism and a sequence of feed forward network. Okay, okay, just like attention mechanism, transform network was also proposed by taking machine translation as the example. So in this paper, attention is all you need, you can see that the concept was proposed by taking MT, okay, as an example. And the transformer network also contains the encoder decoder architecture. Okay, so it has an encoder network as well as a decoder network. Both encoder and decoders are designed using, or defined using, transformer networks. Okay, so it has it doesn't have any sequential nature. Okay, because the networks like RNNs and LSTMs have the sequential nature, and the neural networks, or other neural network, deep neural network, or feed forward networks, doesn't have any sequential nature. So the transformer network is actually designed using a set of feed forward network. Attention mechanism is also designed using a neural network, feed forward network. And apart from this attention mechanism or attention networks, you can find other networks, other feed forward networks in the definition of transformer network. So it is faster than RNN, and it can incorporate the parallelism concept in the implementation. In addition to that, okay, the transformer networks can also capture the long-term dependency, because to capture the long-term dependency, uh, we, with the help of the attention mechanism, okay, the transformer networks can capture the long-term dependencies. Long-term dependencies means, I'll give you one example in the coming slides, so then you will understand what I meant by the dependencies among the data. Okay, so this is one symbolic diagram explaining the working of RNN or LSTM or GRU and its variants. Okay, so we feed one word, and the algorithm will process that word and generate some output, and using those information it can process the next word and produce some output, and so on. So in a transformer, it can receive all the output simultaneously and produce the output also simultaneously. Everything are in parallel. Okay, so this is the architecture of the encoder decoder architecture used for transformer. On the right hand side you can find the complete transformer network, and on the left hand side you can find the encoder network used for designing the encoder network used in the transformer network. So there are a lot of terms you have to consider, but I don't think 1.5 hours is not sufficient enough to discuss each and every concepts in the transformer network, because when we take classes for this transformer networks, it will take 2-3 days to complete the explanation. So there are a lot of concepts related to that. So here you can see that input embeddings, positional encoding, multi-head attention, add or normalization, feed forward network. Okay, then the term nx, it is actually n times. Okay, in a transformer networks you can keep n number of such networks. Okay, so that is a hyperparameter associated with this particular transformer network. So it is not mandatory that you should keep only one encoder in the network. You can have n number of encoders. Similarly, you can also have n number of decoders. Okay, on the right hand side you can find one full complete image of the transformer network, and in that image on the right hand side you can find the decoder. Okay, decoder start with outputs, output embedding, master multi-head attention, add or normalization, multi-head attention, add or normalization, feed forward, add and normalization, linear softmax. Finally go for classification. Softmax actually produces the output probabilities. Okay, you are getting a probability distribution at the output. Okay, so now we are focusing on encoder because the BERT algorithm is based on encoder. So we will discuss some components in the encoder network. Okay, so what are the important concepts related to the encoder network? Okay, so before that you have to consider the concept of input embedding. Input embedding or embedding is a vector. Okay, you can consider embedding as a vector or a point on the n-dimensional space to represent, or d-dimensional space to represent a word. Okay, so that space is called as embedding space. On the right hand side you can find an image which shows the vectors corresponding to each word in the data set. Okay, so input embedding is it is possible to pre-train the embedding space, because if you have a data set, huge data set, you can pre-train the, you can train an embedding model using that data, and which can be used for generating the representation for any other data, okay, or word which is not there in the corpus used for training the network. Okay, so it is possible to pre-train the embedding space, and embedding space maps a word to a vector, so that is obvious. Okay, so the problem with most of the embedding algorithms are, so a word which a word can have or possess multiple senses in a language. So a bank, okay, you can consider it as a river bank or financial bank. Book, okay, in this example I am going to read a book, I am going to book a bus ticket. In the first sentence book is a verb, okay, noun. In the second sentence book is a verb. Okay, so a word can possess different meanings, different senses, different part of speech, etc. Okay, so that is too ambiguous. Language is too ambiguous, so it is not that easy to process a language. That you should understand before starting the experimentations. Okay, so depending upon the context, okay, so I am going to read a book. It is entirely different from the context of the second sentence, I am going to book a ticket. In these two sentences the major difference is the part of speech of the word book. In the first sentence it is noun, and in the second sentence it is a verb. Okay, so that is that kind of computational processing is very, very challenging, and even though book is having different meanings and different contexts, the conventional machine learning algorithms, the conventional word embedding algorithms like word2vec and fastix can generate the similar, same vector for the word book. Okay, so and we have to assume that that vector contains all the different word forms of the word book. Okay, book can have different word forms like book, books, booking, bookings, etc., or booked. Okay, all those words can be considered. Okay, and books can be again, book is a noun as well as a verb. Books are also noun and verb. Okay. So similarly, you can find different senses, different POIs for all the many of the words in the corpus or data sets. Okay, so word to vec and fast text algorithm can generate only one representation for the for a word, and we had to assume that that representation contain all the meanings of the or all the senses of that particular word. Okay, but that is not a very good assumption, because especially when it comes to the Dravidian languages or Indian languages. Okay, so you can generate numerous word forms for a particular word, and you may not be able to find all the word forms of a word in a data set. Okay, so when a new word comes, it is too difficult to find a proper representation for that particular word. Okay, that is the disadvantages of fast text and the word to vec, mainly word to vec. Okay, but in BERT embedding, using BERT embedding, you can actually generate different vectors for different senses. That is also possible. So in this example, book is having two different meanings. Even though book is the same word used in two different sentences, okay, book can have two different meanings. Sorry, two different vector representations or embeddings using BERT. Okay, so this is all about input embedding and how that different vectors can be generated using different vectors can be generated for one single word based on their context. So there comes the importance of positional encoder. So using positional encoder, 1 second. Okay, so the positional encoder captures the position information from the data or the sentence, and it will attach that positional information along with the word embedding. Okay, to make sure that the position of the word in these two sentences are different, and because of that reason, we can generate two different meanings uh, for that particular word, which will help for the further analysis. Okay, so positional encoder basically gives the context-based position of words in a sentence. So in the first sentence, I am going to read a book. The position is 7, and in the second sentence, the position is 5. So based on that con or information, book will be having two different vector representation. Okay, so that is possible now. So depending upon the senses, you don't have to okay, yeah. Based on that context or position, you can generate different embeddings for the same word. Okay, so that is positional encoder, and this is how basically it works. You can generate the embedding. Okay, 0.23, 0.61, etc., 0.35, some random value only. Then you can add positional encoding along with that generated output and obtain the final output. Okay, so which is 0.5 and 0.75 and 0.82. So these are some basic examples to understand the concept. Okay. So this is self-attention is the major concept which is used for designing the or the intuition behind the development of a transformer network is attention only. Okay, so self-attention, there are different kind of attentions, like almost all the attentions are the basic concept is same, but the implementation wise all are different. Okay, the concept is same only. Self-attention, multi-head attention, or multi-head attention is an extended version of the self-attention. Okay, so self-attention is nothing but okay. Before that, I'll revise the concept of attention mechanism. Attention mechanism helps you to focus on certain parts of the input data to predict the output data. Okay, so that is attention mechanism. So in this example, I had a biryani from a restaurant and it was too good. Okay, so what does it refer to? Okay, biryani or restaurant. We know that it refers to okay biryani, but computer cannot understand that it is referring to biryani or restaurant. So we have to. So that can also be. We cannot decide that. Okay, it can predict biryani or restaurant. Okay, because it can match any other word in the sentence. But with the current embeddings, okay, current algorithms, it is possible to learn some kind of meanings from the data. Okay, so we can, I mean, the machine can understand that it is going to compare biryani and restaurant, or it is going to resolve the issues between the, I mean, resolve that problem, okay, between biryani and a restaurant. So we know that it is referring to biryani, but computer cannot understand that. So there comes the importance of attention networks, attention mechanism. So because with the help of attention mechanism, it is possible to focus on the word it. Okay, sorry, it is possible to focus on the word biryani. So when the word it comes, okay. So self attention is also known as attention with respect to itself. Okay. So attention also gives you the importance of ith word in generating the the target word. Okay. So that is self attention. And so do you have any questions related to attention mechanism? It'll be good if you can be a bit interactive.
Participants, if you have any doubt, please ask.
Otherwise, I'll simply talk and I don't know.
Sir,
Okay.
someone is asking something.
Yeah. But,
Sir, I would like to have a doubt. Is it
yes.
possible to have LSTM with attention?
Ma'am,
Is it possible to have LSTM with the attention mechanism? That was
Right,
your
sir.
question. Okay. Yeah, it is possible. We can, I mean, basically thank you for the question. So basically the encoder decoder architecture, we can, in that we are incorporating attention mechanism with LSTM. In addition to that, we can have for applications like sentiment analysis, we can bring attention mechanism with LSTM. So how do we do that is, after LSTM, we add one more attention layer. Okay, we can define in Python. If you are using Python for implementation, we can define a attention class. Okay, so for creating an attention layer, then that can be added as the final layer of the neural network you are going to use, and which helps to focus on, I mean, in sentiment analysis, attention mechanism has a lot of uh, importance, because you don't have to focus all the words in the social media text to implement sentiment analysis. You have to focus on certain words which are really, really important, like the positive words or negative words, etc. So to do that, I think the attention mechanism can help you. So attention mechanism means you can create a class for attention layer. You can use the same class we have discussed in the last class, yesterday's class. Okay, you can use that class for defining the attention layer and add the attention layer as the last layer of the or final layer of the neural network, and train the attention layer or attention network along with the LSTM network. Okay, that way it is possible.
Okay, sir. I have no questions. Sorry
Yes,
for asking. I would like to know, will there be any training time difference, like the model take to train and find accuracy for LSTM, and the model take to time for training and accuracy for an LSTM with attention model? Will there be a variation in it?
yes, if you are using same data, it is obvious that LSTM with the attention mechanism will take more time. Accuracy wise, depends on the data. Okay, we cannot expect that LSTM plus attention will give you the better accuracy all the time. Uh, but in some cases, LSTM alone can give you good accuracy. But when it comes to the training time, LSTM plus attention will take more time to train than uh, uh, model, because in LSTM plus attention, along with the attention, sorry, LSTM, you are going to train one more network, right? So you have to consider the parameters of that network also. So it is obvious thing. Okay, LSTM
Okay.
attention. Okay.
Okay, thank you, sir.
Any other question?
Excuse me, sir.
Ah,
I am
yes.
Bhavna. So self-attention is actually possible with the help of LSTM only, right? Is there any other alternative other than LSTM to implement attention mechanism?
Attention mechanism can be implemented with all the networks, not just LSTM. You can use attention mechanism with the CNN or I mean, DNN. I don't think it is useful, But with CNN also you can use, for example, in object detection from an image, if you want to identify a particular object in an image. So in that case, basically in image processing we use CNN because CNN can give you better feature representations. So to locate a particular object in an image, you can seek the help of attention mechanism. So in that application also we can find the application of attention mechanism.
Okay, sir. One more question, sir. How the transform model is actually dealing with ambiguous words? Is there any separate algorithm we have to implement or it will deal with it, right?
It can deal with the ambiguity to some extent by considering the position information. Okay, depending upon the it is anyway, it is based on the training data. In the example, slide, I have given you one example, right? Like
Yes.
I am going to read a book and I am going to book a bus ticket or what any kind of ticket. Okay, so if you have these kind of sentences in the training data, so the algorithm will learn the position also to generate the embeddings like this. Okay, so this is basic transformer, and in BERT we'll take a few more extra information to generate the embeddings. So if you have this kind of positional information, the algorithm can generate different embeddings for the words which appears in different contexts. Okay, I'll give
Okay.
you
So,
one.
okay,
Yes,
sir. So in the training, sir, we have to include more number of such sentences, right?
yes, yes. Depending upon the data, it
Okay.
can. I mean, you can. Many pre-trained models are available, so you can. It is possible to retrain such models. Okay, you can download the model and retrain the model using your own data. So it is also, if you find that the network is not able to generate the or identify the ambiguity or generate different embeddings for the same word in different contexts, then you can provide more data and retrain the model. So the model will uh, learn new parameters, and based on that it can generate new different embeddings for all the words in the corpus. That is also
Sir.
possible.
Okay, sir. Sir, actually, I'm dealing with Malayalam training data only, so it may work with that also.
Yes,
Oh,
yes.
okay.
Okay, I think I have seen your papers. Now
Okay,
only I
sir.
understood. Okay,
Okay.
you can. There are a lot of pre-trained models uh, available in for. I mean, there is a package called Python package called Hugging Face Transformer. You can find
Okay.
there is no specific package for Malayalam alone. I don't think so, but you can find a lot of multilingual models which can support Malayalam and other Indian languages. So the BERT has the capacity to identify the language also, because it is trained over many languages, and while training, the algorithm itself identifies the language first. Then only it is generating the embeddings. Many of, I mean, uh, MURL, LABSE, BERT multilingual are the names. I mean, are some examples for the multilingual BERT models. I think I can show the website name. So this is the, can you see my screen?
Ah, yes, sir.
Okay,
Yes.
so this is the package. I mean, this contains a lot of data sets, lot of models and applications, pre-trained everything is well documented also. So you can refer to this package for any data. So if you provide any keyword like Malayalam articles, way to web, basically for speech processing, Malayalam wiki data, okay, Malayalam news data. I think this you can download from GitHub also,
Okay.
and lot of Malayalam if you provide Malayalam. Okay, Malayalam models are also there. Okay, speech. This is speech only. Okay, okay. This is hate speech detection Malayalam data speech. Okay, a lot of models are there also. This is classification model, Malayalam BERT. Okay, Malayalam models are also there. Okay, it is
Okay. Thank
keep on updating. Okay, 17 days ago only it got
you.
updated.
Okay.
So
Okay, sir.
okay, you can refer to this packet. I think I can share the link in the chat.
Okay, thank you.
Okay, any other question? Thank you. So we'll move on to the BERT embedding. So BERT, bidirectional encoder representation from transformers. So you can refer this paper for understanding more about the BERT embedding. So it is also from Google. Okay, so the people who developed the transformer network. Okay, Google has one more network which is related to transformer. It is called as Reformer. So you can find a Reformer network in Hugging Face Transformer library. Okay, so BERT. Okay, BERT is a language model. So yesterday I was speaking about language model. Language models have two purposes. One is to predict the probability of a given sentence or a sequence of words, and another task of a language model is to predict the next word given a sequence of words. Okay, conditional probability. Two kind of probability. One is a joint probability. What is the probability of getting a sequence of words? Probability of. So if you want to predict the probability of this sentence, BERT, what is the probability of BERT? Is a language model. Okay, then you can also compute like what is the probability of getting the word model if you are given the words like BERT is a language. So the search engines like Google and the Bingo etc. uses both concepts to implement the for suggesting the search queries. Okay, if you type a few keywords, then it will suggest a few sentences by filling the previous future words. Okay, so for predicting the future words, they use language model, and for showing or for giving you the list of sentences, they'll compute the probability of each sequence, and the sequence with the maximum probability according to your search history, okay, will be shown first. Okay, so BERT is actually based on transformer network, and BERT doesn't use the decoder part. Okay, so basically transformer is an encoder decoder architecture. It follows encoder decoder architecture. Okay, what encoder does? Encoder receives the input data and creates a vector which can represent the entire meaning of the input data or input sentence. And decoder uses this contextual data, vector to generate another sequence of words. That is the purpose of encoder and decoder networks. Okay, so BERT uses the encoder part. Okay, what encoder part does? It reads the data, a sequence of words, and converts every word into some representation, and finally you will get one vector which can represent the entire input sentence. And we assume that this vector, which is called as contextual vector, can represent the meaning of the input data, or it can capture both meaning, or we can call it as semantics and the syntax of the input data. Okay, so the relationship or similarity between BERT and the general encoder, general transformer is BERT uses the same structure of the encoder. Okay, there is no difference, same structure of the encoder. But the difference between BERT and the transformer network is BERT is bidirectional. So why why the people who designed or defined BERT implemented that way, bidirectional version. So in many cases, okay, if you consider the bidirectional context, you can understand the real meaning of a word, okay, or the real sense of a word. So some words, uh, if you want, especially the words like prepositions. Okay, prepositions are very very complicated entity in a language. Okay, so if the meaning of a preposition can be captured effectively when you consider the words which are attached to the preposition, no? After the word, after the preposition, and before the preposition. After the preposition, you can find noun phrases, and before the preposition, you can find verb phrases. If you consider both things, both the verb phrase and noun phrase to which the preposition is attached, then you can understand the real meaning of the preposition. Okay, if you consider the noun phrase only, then you may get more information. If you, I mean, more information means that information will be lesser than the information when you get compare when you use both the verb phrase and noun phrase. So if you use verb phrase alone, you'll get lesser information, and if you don't use verb phrase and noun phrase, then you won't be able to identify a proper meaning of the preposition. okay, in a language. Then if you want to understand the complexity, you just try to translate an English sentence into your native language. Okay, I am going to Kannur. Okay, I am going to the doctor. In these two sentences, how the word to is translated, okay, into your native language. Okay, so the prepositions are very complicated thing, okay, in a language, and to understand the real meaning of or real sense of a preposition, you had to consider both context, or forward context as well as the backward context. Okay, so basically the transformer is unidirectional. Okay, it can pass from the first word to the last, but BERT is designed in as a bidirectional model. It can go from the first word to the last and last word to the first to generate the representation for the verb, sorry, a word. Okay, and because of that reason, it is possible for the BERT to learn the contextual dependencies more effectively than other uh, word embedding algorithms. Okay, and in addition to that, a BERT can contain n number of encoders in it. Okay, so in the general definition of the encoder decoder network, you can see that there is an n times. Okay, so that n times, okay, n can be anything. Okay, in the basic BERT, or the first BERT model, okay, contains 12 such encoders. Okay, so on top of each encoder we stack other encoders. Okay, finally you will get the embeddings for the word. Okay, so context is very important in generating the embedding. So that is the reason why the BERT people used the positional information and bidirectional contextual dependencies to to generate the representation for the, or vector representation for the words. Okay, so these are the given some examples for understanding the importance of the context. So in the first example, word embedding with no context, so river bank and bank deposit. Okay, in these two cases, bank is having two different meanings. Okay, there the word bank appears in two different contexts. Okay, so if you don't consider the context, okay, you will be able to generate only one representation for the word bank. That is not a good intuition actually. Okay, you cannot expect the vector representation can capture or can encode the real meaning of, or the real sense of all the word forms of the word bank. Okay, so that is the disadvantage of that word embedding algorithm, which uses no context. And in RNN and LSTM, you can go from left to right or right to left only. Okay, so that is language modeling. Okay, basic language, neural language modeling, beginning of the neural language modeling. Okay, so you only able to identify the backward or right forward contextual dependency. You can capture either backward or forward contextual information. Okay, that was one disadvantage. But in bidirectional contextual, I mean, the algorithm which uses the bidirectional context. Okay, so you are going to predict the missing word. You are going to mask the word bank, and you will ask the network to predict that masked word. Okay, so by considering the context. Okay, I made a dash deposit. Okay, you are asking the network to predict what is the word with the maximum probability to appear in that particular space. Okay, so based on the corpus or the data set, the algorithm will understand that, okay, bank is going to be the word to be filled in that space. Okay, so in the next case, if in the case of a river bank, okay, so based on that context, the algorithm can predict bank there also, but while predicting the bank there, it will use another representation by considering the contextual information and the position of the word in that sentence. Okay, so because of all these reasons, the training of the neural network, or not the neural network, bidirectional encoder representation from transformers BERT is not that easy. It is more and more complicated than the training of a normal language model. Okay, so there are two training algorithms actually, two unsupervised prediction tasks for training the neural network. One is master language model, and another one is next sentence prediction. So master language model is nothing but we mask a few words, okay, from the sentence, and we'll ask not we, the network will do by itself. Okay, it can uh, the network can it will try to predict the masked words. Okay, then by doing that, okay, then we, while training, it will compare the prediction with the original output, original word, and if there is any error, that error will be propagated back. Okay, then that's how the network gets trained, right? So masked language model is one training algorithm we use in BERT algorithm. Okay, then next sentence prediction. So that is also given a sequence of words. It will predict. We will give, or the network will take two sentences, and the network will ask itself like whether the second sentence is a continuation of the first sentence, or it is going, whether that sentence is going to be the next sentence or not. Okay, it's a kind of binary classification. Okay, we provide two sentences and we'll ask the network to check or predict whether the second sentence is the continuation of the first sentence or not. Okay, so that is, these are the two methods or tasks that we use for training a BERT model. Okay, so there are two steps in BERT training. One is pre-training and fine-tuning. Pre-training means providing a huge amount of data. One second. So a network can be trained using a huge amount of data. Most of the BERT models are trained over common call data and the Wikipedia data, huge amount of data. And once you train the BERT model, you can save the model and you can use it for other purposes by retraining the model. Retraining the model means by fine-tuning the hyperparameters of the neural network. Okay, a network can contain, uh, once a network is trained for one data, using one data, it cannot be directly used for another data, because that the properties of or characteristics of a data may vary, okay, from data to data. Okay, you cannot expect all the data to behave in the same manner. Okay, some data, if you take, if you are doing social media text analytics, okay, then if you take the data from Facebook and if you take data from Twitter, you cannot combine both data, because Facebook data has its own style of writing, and its own sentence creation uh, styles. Okay, then vocabulary usages or usage of words, and the number of words in the post, etc., are entirely different from how we write or post something in the Twitter. Okay, that words will be different, the sentence construction will be different, the number of words will be less. Okay, and which cannot be combined with the social media post you collect from YouTube. Okay, so every social media post has its own property, and it again varies from person to person. Okay, so you cannot use a model trained for one data to use for another data, but we can use it, we use it like that, but it is recommended to use in such a way that you can fine tune the existing models by providing your own data. Okay, so there are other mechanism also, like zero shot mechanism, one shot mechanism, few shot mechanism. There are different kind of approaches are there, but still, okay, if you want to use a pre-trained model for your data, you just retrain the model. Okay, retraining means feeding feeding a new data set to the trained model and update the weight and biases or and other parameters of, basically the network will have two parameters, one is weight and biases, and update the weight and biases by providing the data and adjusting the hyperparameter according to the newly added data. Okay, so that those two things, I mean, you have to do before using a pre-trained model. Okay, so don't expect a pre-trained model to work or perform better in all the cases. Okay, a pre-trained model defined for science data may not work with social media data. Okay, so and a pre-trained model trained over Wikipedia data may not work for social media data. You may get some information, but that information may not be accurate all the time. Okay, but if you don't have any data, you have to rely on the pre-trained models. Okay, so there is no other option. So that is the concept of zero shot mechanism that is used by Google Translate for translating a sentence in one language to another language, because Google Translate can translate any sentence in any language to any other language, right? So if you want to translate Malayalam sentence into a Swahili language, then I don't think you can find a data set which contains the translation of Malayalam in Swahili. So if you don't have any pre-train, I mean, if you don't have any data set, how is it possible to train a network? Okay, so Google uses a mechanism called zero-shot mechanism. Without seeing a single example, it is able to train or predict something. Okay, that is a different case. Okay, again, Google uses BERT and transformers for developing the Google Translate and other applications. Okay. Google, Facebook, uh, all the giants are using transformers for many of their tasks. Okay, how is attention utilized in BERT? So attention to next word. Okay, what is going to be the next word? So there we use the attention to previous word. Okay, to predict the next word, we had to focus on the previous word. Okay, in BERT, attention next word also gives you like you we are computing both bidirectional contextual information, right? So next words context can be used to generate the current word. Okay, so for capturing the both forward and backward contextual information, we have to focus on both uh, previous word and next word. Okay, attention to identical or related word. So for solving the or resolving the ambiguity and all, we had to do this operation. Attention to identical words in other sentences helps in next sentence prediction tasks. So in this example, I had a biryani from a restaurant and it was too good. Suppose if you divide the sentence into two, I had a biryani from a restaurant, it was too good. If you want to connect it with the biryani, then you will have to understand the context. Okay, so that for that purpose also you can use attention. Okay, attention to other words predictive of other words predictive of words. So for predicting the next word, yes, same related to the first point, attention to delimited tokens, CLS, SEP. So CLS and SEP are two tokens that we use to mark the beginning and end of sentences. CLS are, I mean, if you have multiple sentences in a document and CLS is appended at the beginning and end of the sentence, okay, which marks the beginning and end of the data, and separation, the or SEP is used to separate two sentences or two data, so which acts instead of full stop, question mark, exclamation mark, etc. Okay, attention to bag of words or collection of words, okay, which occur more number of times. Okay, so attention is basically doing all these things in the BERT algorithm. So we don't have to do anything. Okay, we just feed the data, and by looking into the data or performance of the model, just change the parameters. That is only work we have to do in this case. Everything will be done by the network itself. Okay, you don't have to worry about anything. Okay, but before applying the BERT and any other any network, okay, especially in natural language processing, you have to go through the data at least once or twice. Okay, understand the properties or the characteristics of the data. Okay, so go through all the data points and see what are the possibilities or what are the possible algorithms we can apply onto this data for the analysis. Okay, so data analysis is very, very important before starting the processing of the data. So the basic BERT architecture contains L number of layers, H number of hidden layer units, and A number of self-attention heads. So L, H, A, and A are arbitrary numbers. You can give any numbers. Okay. Any question? So this is how the BERT generates embedding. Unlike the transformer networks for generating the embeddings, BERT uses some additional informations, okay, also for generating the embeddings. Okay. So in BERT, you can see that CLS, SEP are used for, so sentence is my dog is cute, he likes playing, okay. SEP is used instead of full stop here, and CLS marks the beginning, okay, not for, here it doesn't use CLS for marking the end of the sentence. Okay, CLS is used for marking the beginning. Okay, so here a dog is masked, likes is masked, so that the algorithm will try to predict dog and likes, okay, by considering the contextual information. And hash ing, why it is written like that means, I mean, that the BERT is actually trained using one data. We we cannot expect the BERT to be, or any network to be trained using all the data available in this world. Okay, that cannot happen actually. Okay, we don't know how many data are available in the world. So BERT uses some very small subset of the entire data to train the model. Okay, in language is too complex, and we can expect, especially in Indian languages or Dravidian languages. Dravidian language means the language spoken in the southern part of India. Okay, so these languages may contain a lot of word forms. Okay, for example, if you translate the word she or her, okay, she and her, into your native language, how many possibilities or different word forms you can identify? Okay, in English we had two words, she and her. Okay, in Malayalam or Tamil you can find numerous word forms. Okay, and you cannot expect all the word forms to be there in the data set or corpus. Okay, so in that case you won't be able to represent. So in machine learning, one problem is that it is very difficult to provide a representation for the unseen data. Okay, so that is why we are using unseen data to evaluate the performance of a machine learning model. Okay, so it is too difficult to extract some useful information from the unseen data. So if that particular word is not there in the trained data, then it is too difficult to generate embedding for or representation for the unseen data. So to resolve that issue, what we do now, we divide the words morphologically. Morphologically means we divide all the words into subwords. Subwords is another term. Okay, I'm using all the keywords now. Okay, what it does is we'll divide all the words into the root word and the morphemes. Morphemes are the smallest meaning bearing unit in a language. Morphemes can be affixes, or affix can be a suffix, prefix, and infix, circumfix, etc. Many are there, many different variants are there. Okay, prefix means in the case of embedding. Okay, embedding, ing is a prefix, suffix. Okay, embed is the word, root word, and ing is a suffix. Okay, then misunderstanding, mis is a prefix. Okay, then enlighten. Okay, en is added at the beginning and at the end. Okay, to create the word enlighten. So en is a circumfix which can appear both at the both as a prefix and as a suffix. Okay, then some infixes are there. For example, cupful, that is a word, and the plural form is cups full. So the character s is added in between, so that s is an infix. Okay, so we divide the words into morphemes and root words, so that we expect that all the words in the world at least contain any one of the subwords, okay, in the data set. Okay, so if you cannot find a word in the vocabulary or trade data, then what we do, we find search for the subwords in the uh, model. And if you can't find the subwords, then you will find the embeddings for those subwords, and finally take the sum of those two subwords to generate the embedding for that particular unseen word. Okay, so using these concepts, the BERT will generate embeddings for each word. Then for each sentence, it will create a separate embeddings. And for position also, we'll have different encodings. So for generating embedding for a word using BERT, we use three information. One is token, and another one is sentence, and another one is positional information. So token embedding means basic word representation, and sentence embedding means in which sentence that word appears, and positional encoding gives you the idea like in which position that particular word appears in that sentence. Okay, so we use all these concepts. Okay, the first thing is token embedding, so transforms words into vector representation of the fixed dimension. So to reduce or to resolve the out of vocabulary word problem, we divide the words into segments. Okay, so we can use the embeddings generator for segments to create the embedding for an unseen data. Okay, so all the subwords are basically represented using double hash. And sentence embedding. Okay, so for each sentence embedding or segment, we can keep an embedding. Okay, so sentence embeddings are basically computed by taking the linear combination of the word embedding. So before doing that, we assign some indices to index values to each and every sentence. Okay, so if the sentence index is 0, then we'll go to that and we'll identify the context of that particular word in that sentence. Okay, so and that's how we generate segment embedding. Okay, by taking the linear combination of the word embeddings. And finally we can add the positional information also to generate the word embedding for the for a particular word using BERT. Okay, so this comes the here comes the end of the theory part of transformer and uh, BERT models. If you have any doubts related to BERT, please ask. Now we are going to the hands-on session, okay, of BERT, and I'll give you some examples related to Hugging Face transformers as well. Okay. So if you have any questions, please ask. Otherwise, we can move to discuss the hands-on. Any questions? Okay, you can also type your queries or questions in the chat. Okay, I'm ready to take a few questions, 2-3 questions.
Participants, if you have any doubt, any query, please ask.
Good afternoon, sir.
Good afternoon.
Is it possible for us to create our own encoder, that is to change our parameters in BERT, sir? Is it possible?
Yes, yes, it is possible. So when you look into the configuration of the models in the Hugging Face transformer implementation, you can change the configuration. You can change the number of hidden layers. You can change the optimizers. You can change the loss function. You can increase or decrease the number of hidden layers. Everything is possible.
Okay, sir. If that is being done for our own work, will it be considered as a research work, sir?
I don't think so because just tuning the hyperparameters. I mean, if you can use that model for any other application, then that can be considered as a novel uh, contribution. But
Oh,
just fine tuning the hyperparameters.
it's not.
Uh, I mean, there is no novelty in that, but still you can consider it as a contribution to the research community. You can share your model in the Hugging Face or any other platform and
Okay,
explain that this is being trained on this data and I have fine-tuned the models. But I don't think you will be able to publish a paper based on that.
okay, sir. Thank you.
Okay, thank you. Okay, then we can move on to the hands-on session. So I have prepared two codes, one for explaining the BERT embedding and one for implementing the sentence classification using transformer networks. Okay, that is, I'll be using the predefined classifiers available in the Hugging Face transformer networks. I mean, Hugging Face transformer page or Python package. I think we'll start with the BERT. Okay, so this, hope you can see my screen and all the characters are visible. Okay, so you have to install transformers library in your local system or in the Google Collaboratory. If you are familiar with the Google Collaboratory, you can use the Google Collaboratory for your analysis, and you can install transformers and torch, because transformers can be implemented using both PyTorch and TensorFlow. However, most of the functions or implementations are based on PyTorch. Okay, so you can install Torch in the Google Collaboratory. TensorFlow is already by default, it is available pre-installed in Google Collaboratory, the latest version you will get. Okay, but Torch I don't think you will get. Okay, so there are tokenizer and the BERT model, pandas, NumPy, NLTK, Torch, etc. Okay, so BERT model is used for using a pre-trained model for the analysis. Okay, so model is equal to BERT model dot from pre-trained BERT based uncased. Okay, output hidden states is equal to true, means final states won't be shared or displayed on screen. And there are different models. BERT based uncased is one of the first BERT models published by a Google team. Okay, then BERT based uncased, so cased are there, BERT based multilingual BERT is there. Okay, many models are there, 4 to 5 models are there. Okay, once you define the model, then you can tokenize the sentences, okay, using that pre-trained model. Okay, the way in which that, so it is actually doing, when you call the BERT tokenizer, okay, and the pre-trained model like BERT based uncased, and the tokenizer basically tokenize sentences based on how that model is tokenized and how that model uses the tokenization. Okay, so tokenization is the purpose of splitting a sentence into words and punctuations. So this is our text. Bank, the river bank was flooded. The bank vault was robust. He had to bank on her for support. The bank was out of money. The bank teller was a man. Okay. So now what we do first, we have to do the text preparation. Okay. So for that, we feed the data, input data, and the tokenizer. Okay. That is very important. Okay, so we one correction in a sentence which I made. CLS is, I told that CLS is used for marking the beginning and end of a sentence, but CLS is used for marking the beginning of a sentence only, not the end. Okay, so in all the cases, we have to add the CLS and separator. So if you have one sentence only in the data, then one CLS and one sep will be there. If you have multiple sentences, and the number of sep will be more. Okay, then once you have the data, okay, in NLP, the first and foremost thing you have to do is tokenization. Okay, so some people, some people, they are also from Google, says that tokenization is not required. I think you can find one paper which says that tokenization is not that mandatory in NLP, but 99% of the people uses tokenization. So in that paper also you can find that they use some kind of predefined models or pre-trained models, which is trained using tokenization operations. So basically, the people who proposed the non-tokenization approach towards NL text analysis also uses the tokenization methods, okay, in it. So tokenization is the first thing you have to perform. One of the first steps you have to do, okay, in natural language processing applications. And just like the other deep learning models, we can, once you tokenize it, you can convert, 1 second, okay, you can convert each word into some set of indices. Okay, so we know that the algorithms or the computers doesn't understand text as such, so you have to find a representation. Okay, so before finding the vectorial representation for each word, we convert every word into some index values. Okay, then we design the segment IDs also. Okay, if there are multiple sentences, okay, then length of the indexed tokens. Okay, 1 into length of the indexed tokens. Okay, so that is how the segment IDs are defined, or you can basically give the segment IDs like 0, 1, 2, 3, 4, etc. Okay, so in and most of the NLP tasks we use LSTM, GRU, or RNN and transformer networks. All these algorithms require data in the form of a tensor. So once you clean the data and keep all the relevant information, you can create the tensor by calling toss.tensor of index tokens. Then you can also convert the segment IDs into a tensor. A tensor is nothing but a matrix in another dimension. Okay, in a matrix in 3 dimension or 3rd dimension. Okay, in 2 dimension you can call it as a matrix, and in the 3rd dimension you can call it as a tensor. Okay, so there are tensor processing models are also there. Okay, tensor decomposition algorithms are there. So you can go through those if you are interested. Okay, so token tensor, segment tensor, both the tensors are there. Then we'll return, the function will return after cleaning the data. The function will return the cleaned data. Okay, uh, then token sentence tensor, sorry, tensor and segment tensor. Okay, so token text contains all the tokenized words. Okay, then our next function is get BERT embeddings. It takes the parameters like token tensors, segment tensors, and model. So using this, here you can find implementation. Okay, token embeddings, sentence embeddings, and the transformer positional embeddings. Okay, so we are finally going to use token embedding and segment embedding to generate the final embedding of the word. Okay, so gradient calculation is disabled here. Okay, so you can make it enabled. Okay, for reducing the time only I disabled that with the torch.nograd output equal to model of token tensor segment tensor. So in a neural network we are not using gradient approach to compute the next thing. Okay, so just taking the model output like this, and hidden state is equal to outputs of 2 column to 1 column. Okay, so in the second row, first column, all the elements. Okay, so that's how we obtain hidden state. And so once you get the hidden states, then token embeddings means hidden state can handle a lot of information. So in the final layer only, or final data, you can find token embedding. Okay, then token embedding is equal to toss.seek queues of token embeddings dot, sorry, comma, dim equal to 0. So you'll like combine everything. Okay, or choose the data so that you'll get a single vector representation for the embedding. Okay, then converting torch tensors to list. Okay, you can also convert the embeddings into some list. Okay, so that is also possible. So target word embedding, it is like for text and text, tokenized text, token tensor. Okay, so first what we do, we prepare the data. Then after preparing the data, we start calling other functions. Okay, like get BERT embeddings to generate the embeddings. Okay, in the list token embeddings, we can find the embeddings of each word. So here also, since we convert before generating the embeddings, we started with converting the words into corresponding vocabulary, sorry, indices. So we can retrieve that by calling word embedding is equal list of open list token embeddings of word index, and target word embeddings dot append is equal to, or append of word embedding. Okay, so this is very, very important, and the remaining portions are not that important. It is for another application. So till here you understand what is happening. So this is the most important part. So if you don't have the okay, yeah, not this, like I want to give importance to this also, like text preparation. Okay, actually this is doing a lot of tasks, and yeah, that's it. So this is BERT based embedding. So here we can see that, 1 second, we are generating the word embeddings by considering the segment IDs and token embeddings, but we haven't considered the postal information explicitly here. Okay, so that is one approach, and so this way you can generate embeddings. Okay, you can list out all the token embeddings and get the embeddings for each word. Okay, so this is for computing the distance. Okay, so the bank and bank, okay, you can provide the word bank. Okay, bank and bank are both are similar. Okay, the similarity between the bank and the river bank was flooded, the entire sentence only. Okay, this too low. And the bank vault was robust, that has the maximum probability. Okay, that's it for BERT, and we'll have one more example related to the transformer network. Okay, I'll be using uh, the transformer package for explaining this concept. So pip install transformers. So pip install datasets because the Python package dataset contains a lot of standard datasets, and we are going to use an IMDb dataset which computes the movie related information. Okay, IMB is equal to load dataset of IMDb. Okay, so you can download the IMDb datasets too. Okay, here. So IMDb of test of 0. So basically the IMDb dataset contains uh, the training data, testing data, and validation data. Okay, so we are printing the validation, sorry, first test data. So there are different kinds of tokenizer available in the Hugging Face transformer. Auto tokenizers are there, BERT tokenizers are there. Okay, a lot of different tokenizer algorithms are available. So you can go through the definition and see whether you are able to follow that. I mean, understand that tokenizer concepts. Okay, so it is very easy to learn. So auto tokenizer is one basic architecture or tokenizer we have. Okay. So once you define the tokenizer, then I mean before using the tokenizer, you have to decide uh, what tokenizer you are going to use, what model you are going to use, all those things. So once you define the tokenizer, then next thing is to uh, uh, call the pre-trained model. Okay, pre-trained model in the sense distilled base and case. You can find a lot of pre-trained model. Okay, so in each application, you can see that some models may not work with some data, and some models may work the best in some data. Okay, so here in this case, models. You'll find numerous word forms, sorry, models here. Okay, this distilled XLM robot are large, fine-tuned. Okay, all these language models are actually trained for English and other languages. Okay, very limited amount of models are there for Indian languages. Okay, I'll search for Hindi. Yeah, Hindi word is there. Okay, okay, many models are there. Okay, you can provide the name of the model. Distilled is a smaller version of the BERT original model. Okay, so all the models are, I mean, will be having different set of parameters. Okay, the model you used for one particular application, okay, it is too difficult to use that model for another application. Okay, otherwise you have to retrain it. Okay, so here also we are doing the tokenization. Tokenization is the process of translating uh, a sequence of words into words and punctuations. Okay. Okay. Then once you convert the data into an index or a sequence of indices, then next thing is to make the sequence length equal by padding zeros. Okay. So here also we are doing the same thing. You can see that data collateral is equal to a data collateral with the padding tokenizer is equal to tokenizer. We provide the tokenizer method and it will try to append zeros at the end. Okay. Okay, then we can call the trainer algorithm for train the neural network. Okay, all those things later. Okay, model is equal to auto model for sequence classification from pre-train. So sequence classification can be defined in multiple ways. So that is how we define the NLP models in many cases. Okay, we define the models sequentially. Sorry, we define the model for capturing the sequential nature of the input data. Okay, so here auto model, or I mean it is general model actually for sequence classification from my from the pre-trained model, distributed uncase, and number of labels is equal to 2. Okay, so these are actually basic understanding you should have before calling a transformer networks. Okay, this is the name of the neural network. Okay, so this is the classification task, sequence classification task name. All those things you have to understand by looking into the Hugging Face transformer, because numerous options are there. Okay, uh, so these are the training arguments. Okay, so if the training arguments are by default, you can try to change the training arguments. Okay, training algorithm, output direction or directory, the learning rate, I hope you all know. Okay, the basic uh, implementation of the backpropagation algorithm uses I mean, this backpropagation algorithm, no, we have to use that kind of uh, stochastic gradient descent or other gradient descent algorithms to train the network. So there you can find the application of learning rate, because if you want to update the weight and biases, you can use the equation like W alt is equal to W nu plus eta into uh, delta or do L divided by do theta, where L is a combination of sorry, yeah, L is actually the learning rate. Okay, sorry, L is the lows actually you have to minimize, and eta is the learning rate. So learning rate actually controls the convergence, or what should I say, learning. Based on the learning rate only, the network can decide how fast you have to reach the local optimum, or whether to reach the local optimum or not. Okay, if the learning rate is too low, it will take a lot of time to reach the local optimum of the loss function, and if the learning rate is too high, then you will never reach the local optimum. Okay, these are the cases. And per device train batch, per device evaluation batch, number of training epochs, weight decay, etc. are other parameters. Okay, trainer algorithm is defined as trainer is equal to trainer of model equal to model, args is equal to training arguments. So you can change these training arguments. You can find these arguments in the Hugging Face transformer page for other models and data. Okay, args is equal to training args. Based on this only, it is going to report. Okay, so you can provide along with the training arguments. You can you can provide the training data set, evaluation data set. So why are you using evaluation data set in a neural network? So by looking into the performance training performance, we can decide whether the network is getting overfitted or not. So, or it is, you can also decide whether the network is getting trained properly or not. So evaluation data set is basically used for that kind of checking. So while training the network, evaluation data can be used for verifying whether the network is getting overfitted or not. Okay, so for based on that information, we can fine tune the network and get an improved network. Okay, so tokenizer, you can define the tokenizer data collator is equal data collator. Okay, once you define the trainer arguments, okay, then you can start training the model. Okay, trainer is equal to trade off. Okay, this way we can train the network, and TF train dataset is equal to tokenized IMDb train to DF data set columns is okay. This is not required for our analysis. Okay, this is also not required. This is for comparison only, but we don't require that now. Okay, so this is very important. Batch size is equal to 16, number of epochs equal to 5. Batch size equal to 16 means we divide the data into 16 batches, and we take HU sets one by one. Okay, that is batch size, and number of epochs means the number of times we start from the end of the neural network and coming back to the neural network to the first. Okay, that is number of epochs per second, total train steps, okay, optimal schedule, etc. These are the things we had to define initially. So for classification, we can find a lot of predefined model. So I am using TF auto model for a sequence classification. This is one model, okay, but you can find another other models also in the Hugging Face transformer uh, package. Okay, so import TensorFlow as TF. Model is dot compile optimizer is equal to optimizer. So you can provide the optimizer name, you can provide loss function name also. Okay, then based on the optimizer algorithm, it can be ada data, ada grad, okay, etc. So you can expect that kind of optimizers as the parameters of the compile function. So compile function is basically compiling the neural network and checking for the errors in the code. Okay, then finally once the compilation process okay completed, then we can go for the training thing. Okay, so for training in Python, almost all the packages are using the same function fit. Okay, in scikit-learn it is fit, in TensorFlow it is fit. Okay, in most of the cases the algorithm is going to uh, or the package is going to use a fit function to train the neural network. So while train the neural network, you have to feed a lot of parameters or arguments. One should be the input data and other should be the validation data. Okay, then you can also provide the number of epochs. If you want, you can provide the values or the parameters we have in the other networks also here. Then we can, based on the uh, performance of the model, we can fine tune the hyperparameters like this and make a better okay output. So fit is the function used for training the model. So once you train the model, then you can go for the testing. So similar kind of models are the pre-trained models are there in the I think in the Hugging Face transformer package. I can show you a few examples from that package, Hugging Face. So even Google, Amazon, Grammarly, etc. are using Hugging Face. Okay, I have solutions, docs. So Hugging Face, some examples were there. Data sets. The thing is yeah, here you can find. So these are the models. Okay, Albert, auto classes, BART, BART has BART PHO, BERT. Okay, so depending upon the data you are going to use or you are going to work on, you can choose the different BERT models from here. So if you want to work on scientific data, then SciBERT is there. Okay, then for Japanese data, BERT Japanese is there. Okay, then Albert, CAMA-BERT is for French data. Okay, then so there are different models are there. I don't know, I can remember the uh, all the names, okay, since it is there in the Hugging Face transformer, it is easy to go through the documentation and use it. And then this FNet, I think it is very important because it uses the Fourier transform concept, no, in signal processing. That with it incorporates the Fourier transform with the BERT embedding to generate the new embeddings. I think this is the paper. Yes, mixing tokens with the Fourier transform. See, people are trying different combinations. So if you want to publish a paper like this, then that is possible. You can mix, you can change the theory or implementation of the network, I mean, or the neural network. So FNet uses the Fourier transform concept along with the transformer network. So Fourier transform in neural networks, I think. So this is Fourier transform equation. FNet architecture is an attention-free transform. So again, this is a new uh, revolution, attention-free transformer, okay, wherein each layer consists of a Fourier mixing sublayer followed by a feed for. Okay, so I understood. So in for FNet architecture, instead of the attention plus feed forward network, we use a Fourier. Okay, self attention will be replaced by a Fourier transform layer. Okay, so this is the architecture. So you can compare the architecture with the original BERT architecture. Okay, so BERT architecture is so here encoder embedding multi-head attention. Okay, then only feed forward network comes. So instead of multi-head attention, it is replaced by a Fourier, okay, transform layer. Then yeah, when we tried it, we didn't get any useful information with this model. Then a lot of other models are there. Okay, then GPT-2 is one of the largest networks ever trained. GPT-3 is the largest network ever trained by the human being. So here YOLO, okay, XLNet, XLM, Robota, XL, one of the biggest networks again. Okay, so you can find a lot of application, I mean, pre-trained models, okay, for any many languages. Okay, nowadays people are trying to the recent paper called I think Log to Vec. It's not recent, 2019 paper. Okay. A few days ago only I read this paper. That's the reason why I'm telling this. Okay, Log to Vec actually combines the graphical neural network with the word embedding concepts. Okay, for detecting cyber threats. Okay, so many implementations are coming, and DefNet wave to vec for speech processing, vision transformer for image processing. Okay, so this is from Facebook. Vision transformer is from Facebook. Mini speech. Okay, then these are BERT models. In addition to the BERT model, okay, we can have some tasks also, text classification model, token classification model, question answering model, language modeling, translation, summarization, multiple choice. So many applications are there. Example applications are there. You can directly use those models for your process. Okay. For example, load data set Opus Books. Opus Books is a translation data. Okay. English to French. Okay, you can that website contains the translation from English to many other languages and vice versa. Okay, so this you can directly use the model available in the Hugging Face transformer for translating a sentence into another language. Okay, sequence to sequence training arguments. Okay, output directory evaluation strategy epoch learning rate. Okay, all those things are same. Then trainer is called. Okay, so the similar kind of application. I mean, one we have discussed now for classification. The same thing can be, I mean, same concept is used in translation also. Okay. Then how to run or train on Amazon SageMaker, converting TensorFlow checkpoints, okay, migrating from previous packages, now contribute to transformers. Okay, how to contribute to the transformers. So if you feel that you had a new model, you can go through this document and understand how we can contribute or share our models with the Hawking phase transformer network and model parallelism. Okay, so there is a concept called multi-head attention. So through multi-head attention only we are able to bring the parallelism concept in the in the transformer network. Okay, multi-head attention is directly connected to the transformation. I mean, data transformation. Okay, testing, debugging, exporting transformer models, sharing custom models, checks. Okay, BERTology. Okay, perplexity. Okay. So main classes. Okay, callbacks, configuration, data caller. Okay, so these are internal help. Okay, you can find a lot of things here. So go through this website or package. Okay, for understanding more about the uh, transformer models. Okay, you can find a lot of applications. You can directly uh, use the functionalities available in the Hugging Face transformers. Okay, so this contains general terms related to the Hugging Face transformers, auto-encoding model, auto-regressive model, okay, PLM, causal language modeling. So causal language modeling is a, I mean, it's a probabilistic term actually. So if one event is caused by another event, or if something is caused by another thing, then we can call it as causal. Okay, so masked language modeling. Okay, everything is there. Modeling code is. Okay. So I think this is enough for enough to start with the transformer networks and BERT. Okay, I can share the codes and slides with you. I'll share it with the organizers. You can go through it and you can reach me out at this website if you want to have, and if you want to clarify your doubts related to transformers or BERT or NLP, I can help you. Okay, I may not give you the solutions to all your problems, but I'll try my level best to uh, give and support you in your research. If you want to collaborate also, that's also possible. You can drop a mail to this mail ID. Okay, so thank you all for the patient listening. If you have any questions, please ask related to anything, not just transformers and encoder decoder networks or BERT. You can ask questions related to word-to-word fast or RNN, Lstm, etc. I can take questions from that part also if you want. I think Maya Devi PA has raised a hand. Oh, okay. Maya ma'am.
Ma'am,
Hello. Hello.
So may I ask?
Yeah.
Yeah, actually, I wanted to ask regarding to the whichever links you have shown in WhatsApp, they were all related to NLP.
Yes.
So if my research is basically on networking and attacks in networks, so do we have reference for it also in the same link, or is there any separate site for that?
Network analysis.
Yes, network attacks analysis. For that, I was thinking related to ML and deep learning.
Okay, what I don't have much experience in network analysis, very limited amount of experience. But what one thing I can tell you is, if you have a data in textual format, then you can use any algorithm related to NLP. Okay, if basically if you are analyzing the log files or something like that, if your input is in textual format, then you can try all the algorithms. What you have to do is just fine tune the models. That only required. Okay, fine tune the models according to your data. That's the only thing you have to do.
Okay, sir. Thank you.
You can use BERT or transformer or other RNN LSTM, anything can be used.
Sir, usually it is said that LSTM is executed by sequentially and transformer is more or less parallelism.
Yes,
But
yes.
as you were saying that if we're using LSTM with transformer, the execution time will be more
I
compared to
don't,
LSTM.
I don't think we can use LSTM with the transformers, but we can use LSTM with attention networks.
Okay,
Uh,
okay.
okay, but that also you can try. There is no restriction in applying the different or combining different networks. Uh, but I don't know. I haven't tried it yet, combining LSTM and transformers, and I don't know how it is going to be. But we can. I have tried applying attention with LSTM. That is possible. Transformer is a different thing. Transformer is basically used for implementing parallelism or resolve the parallelism issues in LSTM. So if you try to combine LSTM and transformer, again you are going to have some kind of sequential properties. You are going to deal with that sequential nature of the LSTM networks. So I don't think it will work, but you can make a try. Uh, Again,
Okay, sir.
yeah.
Okay, sir.
Any other questions?
Hello, Premjit.
Yes, ma'am.
Yes, it's not regarding questions. Thank you for being with us here. It's very nice to see in this platform.
Thank you, ma'am.
Dear
It's long.
participants, Premjit is an alumnus of this institute, and for us, it is very proud moment for seeing Premjit as a resource person in this FTP. Thank you, Premjit.
Thank you, ma'am, for inviting me because it's long while since I meet you all. Happy to see you all in this FTP. And I can find a lot of my friends also, I think. Maya Madam, Maya Devi, I worked with her, with JC, Jyoti. I think she left the meeting. So a lot of familiar faces.
Yes, yes.
Okay, ma'am, I'll share the materials and slides and codes with you so that you can share it with the participants.
Sure, sir. Some of them already asked your contact number and mail ID.
Okay, you can share it with them.
Okay, sir.
Okay, ma'am. Okay, thank you.
Anyways, thank you so much, sir. Thank you so much for such an informative session. Sir, someone asked something.
And that's for materials. I'll definitely share with you.
Okay, sir. Okay.
Okay. Thank you all.
Okay, sir. Thank you so much. Thank you, everyone. Thank you for your participation, and we will share you with some overall feedback form. Please fill that, and we have to conduct one test, test regarding this FTP. So we will share some more Google form with a set of questions for evaluating this session. Thank you so much. We will share immediately.
Dear participants, thank you for spending this week with us in this FDP, and all the recordings and materials available will be shared. And let us wind up this session. Thank you for attending these sessions.
Thank you, everyone. We will share that test link and overall feedback link in the WhatsApp group. Thank you so much. Now we can read.